Question 10 from the 2019 Advanced Higher Physics Examination of the SQA. Alpha particles are accelerated to a speed of 5 times 10 to the power 6 meters per second. The alpha particles are then injected into a magnetic field, and the path of the alpha particles is perpendicular to the magnetic field lines. The magnetic induction is 1.7 T, and the alpha particles follow the circular path shown in figure 10a. And for 3 marks, we're asked to calculate the magnitude of the magnetic force acting on the alpha particle. Well, we can put down an equation from that, look up our data sheet, and we get the force acting on the alpha particle is its charge Q times its speed V multiplied by the magnetic induction of the field, which is B. So we know what V is from our question. V is going to be equal to 5.0 times 10 to the power 6, and it's going to be meters per second. We can look up the value for Q, which is the charge in the alpha particle, by using our data sheet, and you can see there, which is ringed, that the charge in the alpha particle is 3.20 times 10 to the minus 19 coulombs. So it's already given to you in the data sheet. So we can mark that down anyway. We can say Q is going to be equal to, in this case, 3.20 times 10 to the minus 19 coulombs. And that's us got all our data. Q, V, and we have got B as well. And we know the value for B. B is going to equal to 1.7 Tesla. So it's a simple case of putting in all the numbers and working it out in your calculator. It's going to be 3.20 times 10 to the minus 19 multiplied by the value of V, which is going to be 5.0 times 10 to the power 6, and then we multiply that by the magnetic induction 1.7. So we work that out on our calculator. We come up with an answer of 2.72 multiplied by 10, and it's going to be 10 to the minus 12 of a Newton on our calculator. So that's the first 3 marks done quite easily. 10a Part I continued. Part B. The magnetic force provides the centripetal force that causes the alpha particles to follow the circular path, and we're asked to calculate the radius of the circular path for 3 marks. Well, we do know already that we have the following. We have that for a centripetal force, F must be equal to the mass times the speed squared divided by the radius. That's the definition for the centripetal force. Now we have to find R, so we simply cross multiply, and we get Fr is going to equal to mv squared, and to find the radius R is going to equal to mv squared all upon the force. So that's us rearranged everything to find the radius. One thing we have to do is find the mass of the alpha particle. Once again, we go to our data sheet at the beginning of it, and you can see it circled there. The mass of the alpha particle is 6.645 times 10 to the minus 27 kilograms. So we can put that one down then for the mass, and all we have to do is write that down. Mass of the alpha particle is going to be equal to 6.645 times 10, and it's going to be times 10 to the minus 27 kilograms. And we already know the speed of the alpha particle entering into the magnetic field. It's 5.0 times 10 to the minus 6 meters per second. And the other thing we know is the force, which we calculated in the previous question. The force came out to be 2.72 times 10 to the minus 12. And that's going to be newtons for the force. So that's us got all our data, so we can plug that into our equation. R is going to equal to the mass, which is going to be 6.645 times 10 to the minus 27, multiplied by v squared, so we're very careful, 5.0 times 10 to the minus 6, and we have to square that, so always make sure that's squared in your calculator. Close the final bracket and divide that by the force, and the force was 2.72 times 10 to the minus 12. So we do that in our calculators, we end up with the radius to be 6.1 times 10 to the minus 2 of a meter, and that makes sense. Times times 10 to minus 2 of a metre. So that's us worked out the radius of the alpha particle circle in the magnetic field. Question 10, part 2. The alpha particles are now replaced by protons, and the protons also travel at a speed of 5 times 10 to the power 6 metres per second and are injected into the magnetic field at the same point and in the same direction as the alpha particles. Now we're asked for 3 marks to sketch on figure 10a, that's your question diagram, the path followed by the protons after they enter a magnetic field. Well, here's a coded program showing you what in fact is happening. The red circle is for a proton injected into a magnetic field, and the blue circle is for the alpha particle. The magnetic field is out of the page, as you can see by the arrows pointing towards you, and there's the 2 circles which the 2 particles make in the magnetic field. The red path is the path of the proton, and the blue path is the path of the alpha particle, and you can see they both prescribe circles. Now that was made up from a code from VPython. It's very important if you're doing advanced physics in future, even university physics, to get involved in coding, because when you do some coding, put down the proper equations, you can actually visualize what's happening. So there we have the 2 circles prescribed. One thing you also notice from that is that the time it takes for the proton to make 1 complete circle is in fact half the time it takes for the alpha particle to make 1 complete circle. So have a study at that diagram. You can see the magnetic field pointing out the way towards us. The proton has made 1 complete circle, and the alpha particle is just catching up there to make its 1 complete circle, while the proton has made 2 complete circles. Now we have to look in terms of radius, as it said here, so we have to take a look at the equations and the data involved for a proton and for a neutron. So here's the situation. A proton, we'll call it mass mp, and it's got a charge qp. The alpha particle is made up of 2 protons and 2 neutrons, and that gives that a charge of 2+. So you can see that the 2+ charge here due to 2 protons. So we can say the mass of the alpha particle is 4 times the mass of the proton, and the charge of the alpha particle is 2 times the charge of the proton. Now let's look at the formula which gives us the force acting on the particles in the magnetic field when they're travelling at a speed v. And we know that's given us F, force. The magnetic force is going to equal to Q, the charge in the particles, times the speed of the particle, times the magnetic induction B. Now that's the force that's going to give rise to the centripetal force. Remember, the centripetal force doesn't come from nowhere. The centripetal force is caused by this force here. And the centripetal force is equal to the following. It's equal to F equal to mv squared divided by r. Now if we equate those 2 forces together, we can have an expression for the radius. So we can have Q VB is going to equal to mv squared divided by r. And we just simply have to cross multiply by the r and cancel out a v, so r QB is going to equal to mv. So we can rearrange to find the radius, and it's going to be mv divided by q times b. Now, as was said in the question, the speed and the magnetic induction for the field are exactly the same. So really the radius is going to depend on the following. The radius is going to be equal to some constant k, which we'll call k, and it's going to be times just simply m divided by q. I've just made a constant out of the speed and the magnetic field b. So let's look at the 2 different radius which is arrived at the particles in a magnetic field. We can say that the radius of the alpha particle is equal to that constant k times the mass of the alpha particle divided by the charge on the alpha particle. And we can say that the radius of the proton, p, is equal to that same constant k times the mass of the proton divided by the charge on the proton. So that's what we've got. Now we can take a ratio now. We can say that the ratio of the radius of the alpha particle divided by the radius of the proton is going to equal to, in this case, the 2 k's will cancel. You're going to have m alpha over Q alpha divided by, and going to be MP over QP. The two constants K cancel. And we have the following: M alpha divided by Q alpha. And that's going to be multiplied by, remember, if you're dividing by a fraction, you invert it. So it's going to be Q times P, charge of the proton, divided by the mass of the proton. So that's what we've got then. We've got a ratio of the radius of the alpha particle's path divided by the radius of the proton's path. And it's going to be M alpha over Q alpha times QP over MP. But we know the relative size of these. We know that M alpha is going to equal to 4 times the mass of the proton, so we can change that to 4 times the mass of the proton, and divided by Q alpha, the charge on the alpha particle is going to be 2 times the charge on the proton. And that gives a nice little sort of kind of like cancelling out exercise, QP over MP. So we cancel out, we have MP cancelling with MP, the mass of the protons cancel, and the charge of the protons cancel as well, and we're left with 4 over 2. And therefore we can say that the radius of the alpha particle over the radius of the proton is 4 over 2, which is simply 2 over 1. So therefore we've proved it algebraically. We know that the radius of the alpha particle is going to be equal to twice the radius of the proton. Question 10 continued, Part B. Cosmic rays travel through space towards the Earth, and approximately 9% of cosmic rays are alpha particles. Alpha particles that enter the magnetic field of the Earth follow a helical rather than a circular path. And for 2 marks, we're asked to explain why alpha particles travelling through the magnetic field of the Earth follow a helical path. Well, here's an example of a helical path. It's a path which starts off as a circle but kind of moves upwards, very much like a parking lot, where a parking space where you start at the bottom, you drive round the circle, but you're moving up all the time. That's what we mean by a helical path. This here is what we call a circular path, as shown there. But why does this happen in a magnetic field in the Earth? And the reason being that the particle that enters into the magnetic field will be entering into the magnetic field at an angle to the magnetic field. In this case, you can see that the velocity vector is at an angle to the B field vector. Remember, that is the magnetic B field vector here, B. So you can see both of them are at an angle. And it's because of that angle that you'll get this helical motion, because we can break that velocity vector into its components, and one of the components will be in fact perpendicular to the magnetic field, and it's that component which gives rise to the circular motion. So if that was just the only component we were dealing with, you get circular motion like that, and that's going into the page and back out again, into the page and back out again. But because we can put in the other component, which will be parallel to the magnetic field, this will not cause circular motion, but cause the particle to move up. So you're getting that circular motion moving up like that, and that will translate as something like this. You'll have the circular motion moving upwards in a helical path as shown, and that's why we get the helical path. The simple answer being you have 2 components of the velocity. You have one perpendicular to the magnetic field, which gives rise to circular motion, and you have a component which is parallel to the magnetic field, which doesn't give circular motion. There'll be no magnetic force acting on due to the velocity parallel to the magnetic field, but will cause the particle to move up the magnetic field. So that's why we get this helical motion, and we can see that in the following simulation. So here's the particle moving in the magnetic field, which is straight up the page. It has 2 components. It has, first of all, a perpendicular component of velocity to the magnetic field, and that's causing this circular motion. Remember, the particle is coming in at an angle, therefore the velocity of the charged particle is at an angle to the magnetic field. The other component is the component of velocity which is parallel to the magnetic field, and this results in the particle moving upwards along the direction of the magnetic field lines. It won't have circular motion. So it's a combination of these two components, the vertical component of the velocity, which will be in fact parallel to the magnetic field. That will cause the particle to move upwards, as we can see there. And it's the perpendicular component of the velocity to the magnetic field, which will cause a circular motion. So you're having circular motion being moved gradually upwards, very much like a car going into a parking garage in the town centre. It starts and the front floor goes round the circle, but the floors slowly rotate upwards to the top. And that's how the particle enters into the magnetic field and displays a helical motion. It's because there are two components. Question 10 continued, Part C. The Pierre Auger Observatory is a large cosmic ray observatory in Argentina. The location of this observatory is shown in figure 10b. Now, the observatory is placed at an altitude of 1,400 metres. And for 2 marks, we're asked to explain why this is the choice of location for the observatory was preferred to locations at lower altitude and to locations closer to the equator. We'll take it in 2 parts. First of all, the reason why it's built in a high mountain is because the higher up the observatory is, the better chance there is of capturing cosmic rays. The cosmic rays will have less atmosphere to pass through. Of course, the more atmosphere they pass through, the more the cosmic rays can break up into other particles. So below a certain height, you might not receive any cosmic rays. So that can be summarised in this diagram here. There's the Earth and there's the mountain on top of it. The green dotted line represents the level where it's harder to detect cosmic rays, and they can see that the cosmic rays will be much more collectible at the top of the mountain because they've got less atmosphere to pass through. So that's the simple answer to the first one. The second one is to do with the fact that the Earth's magnetic field is shaped like this. If I can draw a diagram here, there is the Earth's magnetic field. You can see at the equators the magnetic field lines are not very close together, but at the poles they are quite close together. So if you're very close to the southern pole, you'll be down here where the magnetic field lines are close together, and that means that any cosmic rays will tend to spiral into that area rather than at the equator. So the reason why it's chosen to be near the south equator is because the magnetic field lines are stronger there, and the incoming cosmic rays tend to bunch into these areas here. Similarly, at the north pole, the cosmic rays tend to bunch up into here. And that's why we get that beautiful aurora borealis, because of the cosmic rays gathering at the poles. The magnetic field at the equator is not strong enough to collect these cosmic ray particles.